torque is going to be induced. So the first part, power generation is based on voltage generation, right? Based on voltage induction. In the armature windings of a generator. So whenever you have a generator, there should be an armature winding where voltage would be induced in that armature winding. So an armature winding is there, then through an external magnetic field. If I have basically my armature winding kind of rotate or change its movement inside that external magnetic field, that will induce voltage across the sides of that basically armature winding. In its simplest case, you can have an inductor bar, a conductor bar like this. That conductor bar is going to move. You can move it left or right. And in order for basically that circuit, electric circuit, for that conductor bar to close, you have to have like this path, right? So this path, as you can see, as you move your conductor to the left and right hand side, there would be a flux. So this is a magnetic field. Here is an external magnetic field is shown through that B vector, which is out of the page. So it is directing out of the page. And then inside that magnetic field, we have this conductor bar. This conductor bar can close its path through these other conductor bars. Okay, but we're going to move this conductor bar to the left and right hand side. So technically, when you do so, you're moving your conductor bar inside that magnetic material, or inside that magnetic field. So the rule by which a voltage would be induced on the sides of this conductor bar would be based off of this external product of V times B, which is going to be internally produced by the L vector. Let's see what these are. V and L are the velocity and length of the straight conductor. So this V is the velocity or the speed of this conductor bar through which you are moving it to the left or the right hand side. So here I'm moving it to the left hand side based off of this picture, right? Okay. L is the length of the conductor. So this conductor has a length of L. The vector L, so when we're talking about the length, I put a vector sign on L, which shows that L is technically a vector. That vector, well, the direction is in a way that it points to the positive polarity of the voltage. So if this is the positive polarity of the voltage that would be induced on this bar, L vector, this is vector L, would be a vector that its magnitude is equal to the magnitude of the length of the bar, and its direction is in the same way as the positive polarity of the voltage that is going to be induced on this bar. Okay, now we'll talk about basically what polarity should be later. And direction of the L is such that it makes the smallest angle with respect to the vector V times B. So look at basically V. Look at the vector B that is coming out of the page. So apply that V times B. The direction of that V times B would be this vector. This is another way to express this. So I meant that this L is pointing towards basically the positive polarity. But another way to come up with the direction of that L is that you find the direction of V times B, and in this case, the direction of V times B came up like this, okay? And then you have to look at basically the smallest angle that is going to be produced by the, through these intersection of these two vectors. So this would be the smallest vector. So L's direction should be in a way that it creates that smallest vector. In other words, if I put L's direction to the other side, it will make a bigger angle with respect to V times D, right? V times B. So therefore, this must be the direction of it. So this is one thing that I wanted to mention here. The next thing is that How do you find the direction of B plus product produced by B? In order to do that, you have to basically use your right hand. If the index finger of your right hand basically points to the direction of B, and the direction of your middle finger points to the direction of B, then the direction of your thumb would be the direction of B cross B. Does that make sense? So use your right hand, point your index finger on B, middle finger on B. Your thumb should be in the same direction as B cross B. Okay, so keep this in mind. And let's look at here. The movement of the conductor increases the area of the closed loop, or in other words, the lambda over dt increases. So, I mean, we're talking about this rule for producing the voltage, but we also talked about E induced is coming out of basically the lambda over dt, or the changes of the flux linkage over T. So flux linkage is the flux that links basically the whole magnet, the whole circuit. So the lambda over dt will increase. If you go to the left, this area is the area that links basically your conductor with the rest of the circuit, right? So if you move it to the left, d lambda over dt will increase. So based off of this, the direction of the electric current should be, so if there was basically a path for electric current, which is going to be this path, because this is the closed path. The other path is not closed, right? So this is the path through which the current can flow. The direction of that electric current should be in a way that the resultant magnetic field opposes the increase of d lambda over d. So this is talking about another way to explain why the polarity of the voltage should be here on the upper side of this bar. That's because, based on the Lenz's law, when you put this moving conductor inside this magnetic field, external magnetic field, it will result in a current in the conductor, right? That current will produce its own magnetic field. And that magnetic field that is produced by this current, based on the right-hand rule, take your finger, take your thumb in the direction of the current. Your four other fingers would basically show the direction of the magnetic field. Now, if you do so, you will see that the resultant magnetic field, because of this current that I've shown in basically a green arrow, will be opposing basically the originating magnetic field, which is out of the page, right? So this is another way that you can explain why the polarity of the current should be like this. So one easy way would be to find the polarity of the current in the same direction as the L vector. L vector should be in a way that it produces the smallest angle with V produced by B. So this is one way. The other way is that if there was a current going to be flowing in the closed path, it should produce a field which would oppose the originating field of B.
We talked about the fact that if you have a conductor bar in front of an external magnetic field, if you move that conductor bar, there would be some voltage induced on the sides of that conductor bar. So the example was here. So here you have your magnetic field out of the page. This is the bar that you're talking about. Your bar can slide to the right or left. And here in this example, I'm moving that to the left. Because of that movement, you can see that the linked flux, this is the linked flux. The linked flux is the portion of the flux that can be linked with your basically electric circuit, so that you can provide a basically closed path of electric current because of that. So this is the portion that you can see is going to increase as you're moving basically your conductor bar to the left. The flux linkage, or the flux, is going to increase, the flux that goes through that closed path. So therefore, the current that will flow into the circuit should be in a way that it decreases that flux, because flux is increasing, external flux is increasing. Now, if the polarity of the voltage would be positive on the up and negative on the downside, then the right-hand rule is that you put your thumb in the direction of the current, and the current goes from the positive to the negative sign, right? or the positive terminal to the negative terminal. If you put your thumb, you will see that the result would be the 4 other fingers, which would oppose the originating magnetic field, right? So that's how you determine. This is one of the ways that you can determine the basically direction of that current, or basically the positive negative polarity of the voltage in that conductor. Now imagine that instead of basically moving that bar to the left, you're going to move that to the right. When you move it to the right, your flux is going to decrease, right? Because that closed path is decreasing. That closed. So therefore, the polarity should get reversed to increase. Basically, the current would be the other way around, so that it tries to increase now the flux. So that's how you can. The next principle was the principle of motor action. So again, we have an external magnetic field. In that magnetic field, we have a current inside a conductor. So that current inside the conductor should be obviously provided through a circuit, right? But we're just talking about that portion which is represented by this conductor bar. There is a current flowing in this direction. Now, because of the current inside that conductor, there would be a force induced on that conductor bar because of that external magnetic field. And the direction of the force would be determined by, and the magnitude and direction of that flux would be determined by this formula, 518, which is showing the force. The force would be I times L vector cross-produced by the B vector. So the current would be in the same direction as the L vector. So if you're wondering what the direction of the L vector is, that's in the same direction as the current's direction. So now let's use basically our 3 fingers of the right hand.
All right, so let's go to example 5.4. In this figure, we have a flux density which is equal to 1 Tesla, and the conductor's length is 50 centimeters. If the conductor moves with a speed of 3 meters per second, how much will be the induced voltage on the side of the conductor if the angle between V plus B and the conductor would be 30 degrees, if this angle would be 30 degrees. So we first need to find V cross B. V cross B will have a magnitude of VB times sine of 90 degrees, and 90 degrees is the angle between V and B vectors. V and B vectors are 90 degrees apart, right? So this comes from there. And then you have your L and cosine. So because of this internal multiplication of these 2 vectors, so this will make one vector. This is another vector. When you basically do the dot product of these 2 vectors, the result would be basically the magnitude of this vector, which is VB sine of 90 degrees, times the magnitude of the L vector, times the cosine of the angle between the 2, which based on the problem statement is 30 degrees. Okay, so this gives you an idea of how the voltage can be produced. So the whole concept of electric generators is based on the fact that some armature windings, would be rotating inside an external magnetic field. So therefore, voltage would be induced on the sides of the armature winding, and that's the principle of voltage generation. The next concept is the principle of motor action. So how do motors work? So all of the electric motors work based on this principle that a mechanical force will need to be induced on a current carrying conductor when it's in the vicinity of a magnetic field. So again, look at same kind of example. Here, instead of moving basically your conductor, you're going to create a circuit that will result in the flow of a current in that conductor. Okay? Because of the current flowing in that conductor, there would be a force induced on that conductor through that external magnetic field of B. And that force would be based on this. That force would be I, which is the current inside that conductor, times L cross B. L, where L is the vector associated with the length of the conductor, and B is the external magnetic field, and L vector has a direction which is in the same direction as the current. So if the current flows from bottom, basically lower part to the upper part, then that L vector should be considered in the same way. Now let's go ahead and apply basically the right-hand rule that I just mentioned to that L cross B and see how the direction of the force should be, the force which is the result of this. So we use the right-hand rule. Our index finger should be aligned with L, okay? Your middle finger should be aligned with B. Go ahead and do that. Then your thumb will show the direction of F, which, as you can see, would be in this. So if you put this bar and put current inside this bar, there would be a force induced on that conductor. That's the principle of motor action, because force will produce a torque. If for example, if one side of this bar is anchored, that force will produce basically a torque that could potentially rotate basically this bar in the clockwise direction. Isn't that so? All right, so that's the principle of motor action. Okay, there is another example in here, which is talking about calculation of induced force on a current carrying conductor. So if in the example that we had before, we have a bar that is carrying a 0.2 amps of current in this direction. How much force would be? So you should find out L times B times I. So this is your I. This is your L, which is 50 centimeters or 0.5 meters. And this is T. And since L and B are perpendicular with one another, the sine of the theta between them would be sine of 90 degrees equal to 1. So the induced force would be 0.1 Newton, and the direction would be determined by the right-hand rule, as I just explained.
This is talking about a wire that is carrying a current in the shown direction. We want to find out the magnitude and direction of the force induced on the wire. Okay, let's talk about the force, the direction of the force. How would that be? The direction of the force would be I times L cross product by B. That would determine the direction of F. So means L should be in the direction of the current, right hand. First element L would be the index finger. Second element would be B. In which which finger? Middle, right? So index finger would be in the direction of the current. Middle finger would be in the direction of the field. So force would be going into the page, right? Right? Force is going into the page. If you reverse any of these vectors, then you would reverse basically the direction of the force. So if the B is from right to left, the force would be out of the page. If you change the direction of the current, again, it would be. If you change both, it would go back to into the page. Showing magnetic field, we're talking about now the polarity. Let's, in two different cases, when this angle is 45 degrees, right, as it's shown, we want to find the polarity of the induced voltage. So the polarity of the induced voltage would be E induced would be V times B dot produced by L, right? So let's try to see it in different ways. So V and B, you have the direction of V, you have the direction of B. Let's use the right-hand rule. So V would be in the direction of your index finger. The middle finger would be in the direction of the magnetic field. So your thumb would indicate the side of the positive polarity, which for us, it should be here. Positive polarity should be here, right? So let's make sure we understand that. If this is the positive polarity side, this would be the negative side, right? The direction would go from the positives through the external circuit, come back through the negative. So this would be the direction of the current. So if this is positive, this is negative, this should be the direction of the current, because there should be an external circuit where it takes the current through these wires and then brings them back. So this would be. Now, if you have this current in that direction, use the right-hand rule to determine the direction of the produced magnetic field. If you have it that direction, then you see that it turns and wants to go out of the page, which would be in opposite direction of the field that we have here. So that's correct, right? The positive polarity should be here, because it will produce a current that it tries to basically make a field that goes out of the page, as opposed to the field that right now is going into the page. Okay, so and in terms of calculations, just depends on that degree, because that would be V times L. So if you look at, you would have V times B sine of theta. Theta is the angle between V and B. The angle between V and B is how much? V and B. 90 degrees, right? So this would be sine of 90 degrees. And we have L times cosine of the angle. So the cosine of that angle is 45 degrees, right? So depending on what that angle is, that could change. If the angle becomes 90 degrees, that becomes minimum, which is 0. If it becomes 0, it will become maximum. Cosine of 0 is maximum, 1 equal to 1. So as you can see, it depends really on the location to determine the exact force.
Let's talk about the general definitions in electric machines, whether they are in the form of a generator or in the form of a motor. So although different types of electric machines can vary in design, manufacturing, there could be AC, there could be DC, or any other form, but there are certain parts in these machines that are common in concept. Okay, first thing is field. You have to have a magnetic field in every machine in order to operate, whether that's a generator or a motor, doesn't matter. You have to have an external field. So existence of that magnetic field would be essential. That required magnetic field, depending on the machine type, will be produced using a field winding, so a special circuit that produces that magnetic field for you. So we know that if you have current inside a winding, that would produce a magnetic field. So that field can be produced by that circuit, or we could use sometimes permanent magnet for that purpose. So certain designs, machines would be permanent magnets. That external field would be produced by that permanent magnet. In some other types of machines, that external field will need to be produced by that field one. So that field is really essential. Then you have armature winding. The armature winding is the part in the machine where if machine is working as a generator, is that part of the machine where the voltage would be induced in? Or if the machine is working as a motor, would be that part of the machine or that winding where torque would be induced on, right? So electric machines have two types, motor or generator, right? If they're motor, there would be somewhere that rotates, right? Somewhere where rotates, and that rotation is because of the induced torque. Now, armature winding is where that torque would be induced on. It has to be a winding based off of this ruling here. So a collection of these bars could be producing a winding for you. And when you put that collection, which you call it armature, inside basically a magnetic field, it would produce a torque through that magnetic field on that collection, which you call it armature winding. Now, if you have a generator, that collection of windings would be the collection where the voltage would be induced on based on this rule. So really the concept goes back into these two rules, the voltage induction and force induction, or basically a force which will be converted into a torque in rotating machines. So that's the field and armature. Field is where the external field is produced. Armature is where the voltage would be produced or the torque would be induced. And then we have the stator. The stator is any part of the machine that does not move in space. Those parts will be collectively called the stator of the machine. And the rotor would be those parts which will be moving or will be rotating. That collection would be called the rotor. Now, sometimes in certain machines, the stator would be on the armature winding. Okay, sometimes rotor would be on the armature winding, depending on the type of machine. We will see that when we go to different types of machine later on. These general diagrams could give you an understanding of where the power comes from, where it goes to, and where are the different sources for loss in your electric machines. So look at this upper diagram. This is showing the power flow in a motor, in an electric motor. In an electric motor, we give the motor electric power, right, on the input side, and we receive mechanical power on the output side. So electric power would be given, mechanical power would be resulting. Now, between these two, there would be some deviations of power, as we can see. So first of all, your machine would have some copper parts where the windings are located. Those would have their own losses. We call the losses associated with those currents that are flowing inside those windings copper losses, or PC. Remember when we talked about the core or the magnetic core, there would be some losses associated with them, depending on the magnetic material. And those losses would be in the form of hysteresis loss or eddy current loss, right? So those collection of losses together are called core losses. Then your machine has some rotating parts that have friction with respect to one another, right? So those frictions would be either between solid parts in the machine, which we call them P friction, PF, or would be between the rotating parts and the air. There would be some friction with respect to the air as well. So we call those windage losses. So friction and windage. Windage is the friction with the air. So those would be the mechanical losses in the machine. And finally, no matter how much we try to basically count for these types of different losses, there would be some difference between basically this loss. So in principle, I must say that if the machine is based on this in the motor, P in minus PCU minus P eddy plus P hysteresis, minus P friction plus P windage. That should be the output power, right? But this is not exactly correct. So we have to account for some losses that cannot be really modeled, a kind of anonymous losses. And those we call P stray. So those P stray losses could be up to a few percentage that will be the output power, the result of this calculation. Okay, so these stray losses could go up to 1%. So if you do your calculations even very correctly, there are some parts of losses that are not modeled or cannot be modeled. We call them stray loss. If you have a generator, the reverse of the power would be just the flow of the power would be just reversed. So you give mechanical power to the generator and you receive electric power on the output. So there would be some losses, basically stray losses, mechanical losses, core losses, and copper losses that would be deducted from this to give you the output power. Now, on the mechanical side, the mechanical power
which we call it PM, is equal to the torque, the mechanical torque, times omega m. Omega m is the mechanical rotational speed. Okay, so PM is equal to tau m times omega m. That's something that you need to remember. But we have another torque, which is called the electromagnetic torque. So the torque that is resulted from the induced force in a magnetic field is called the electromagnetic torque. On the other hand, the torque that is applied through the shaft of the machine is called the mechanical torque. There is a bit of difference between these two in terms of numbers, and that's associated with the losses, with the friction losses, the mechanical losses of the machine. So the power that is resulted from the electromagnetic torque, we call it the converter power, the power that has been converted through the magnetic field and the electromagnetic process. But the real power that reaches the shaft would be the mechanical power. That the difference between these two is some losses, the mechanical losses. Now, that difference makes the difference between the electromagnetic torque and the mechanical torque, as you can see. Omega m would be the same in both cases. Now let's go to this example 5.6, which is talking about the power losses in an electric motor. You have an electric motor in which the electric power measured at the motor's electric terminals is 110 kilowatts. For the motor, the input power is electric power. You're measuring that electric power at 110 kilowatts through a watt meter, for example. The motor is running at 1250 RPM. That 1250 is your omega m, right? Omega m, nm. So the way that we talk about rotational speed, when we talk about n, we mean the unit is RPM, revolutions per minute. When we talk about omega, we mean radians per second, right? So in other words, in this problem, your nm is 1250. We have an overall efficiency of 90% in our machine. Assuming that the core losses are 3,000 watts and copper losses are 7,000 watts, we want to determine how much are the mechanical plus stray losses in the machine, how much is the load's mechanical torque, right? So this is easy, really. This is based off of the same flow of power diagram that we have for the motor. We're given the input power. We're given basically copper losses and core losses. We're asking for these two together if the efficiency of the machine is given. So the efficiency would be PM over P in, right? P out, which is the mechanical power, over P in. So here we're having some symbols. P in, input power, NM, the mechanical speed, efficiency, core losses, copper losses, and the outputs are PMS, which is mechanical plus stray losses. So this comes right from the definition of efficiency. So P output would be the efficiency times P input. So from here, this is coming from the definition of frequency. Now, if you look at the power flow, P in minus PCU minus P core minus PMS becomes PM. So if you just replace PMS, PMS means P friction plus stray losses. That would be found. And this is the first part of the problem where you can easily find the PMS. The second part of the problem is how much is the load's mechanical torque? So if you're given the output power, and if you're having omega m, you can find out the mechanical torque, right? So that's omega m. Make sure that you find the omega m radians per second by multiplying nm times 2 pi over 60 to find basically the right value of the mechanical torque. So when you do this problem, you get PMS would be 1,000 watts, and tau omega m would be 0.76, 7563 Newton meters. A motor is supplying tau Newton meter of torque to its load. If the motor shaft is turning at certain RPM, what would be the mechanical power supplied to the load? So this is just very easy. I just wanted to show a way. I'm expecting you to show me basically the numbers using the display command. It's really easy to do that. And I also want you to pay attention to the units. So Here P is in watts. So this means that you have to create basically a P in watt here for me. P in watts would be what? Would be your tau in Newton meter times omega. And omega would be what? Would be Nm times 2 pi over 60 to make it in radians per sec, right? So that's how you need to calculate this one. And once you find the in watts, you can find it in horsepower by just dividing that by 746.